Hello children. So we're finishing up momentum today. All we have is just two very juicy problems. So let's get started. Okay, so one of the ideas for today's lesson is basically combining momentum and energy. Yet you realize they're not the same, they are different, don't mix them up. But in some problems you can use both. I showed an example last lesson. We'll look at some more examples today where it's a little more complicated. Here's a nice video.
Tough world.
Okay, not much to say about that. I guess like the explosive charge the that fires a bullet that a gun uses gives off a certain amount of energy. So look at the energy in K, 1/2 mv squared. So you could have a pretty small mass and give it a large velocity. That's how most guns work. A bullet has a small mass, large velocity. But in that video, there's like a big block of iron or something. Much higher mass, much lower velocity from the same amount of energy. Why might that be useful, that thing? Well, you can use the same amount of energy if you have, if you have a small mass and a large velocity like a bullet, it can have the same energy as a big block of iron at a lower velocity. Which one would have more momentum? If a bullet and I guess it was called a battering ram attachment, ram, ram, both have the same K, which one has more P? What do you think? If they both have the same K, a bullet will have less momentum, the battering ram will have more momentum. Because for a bullet, the speed is bigger and the speed is a bigger effect. Here speed is squared, here speed's first power, so the battering ram in the video had more momentum. But we'll look at an example of something that has momentum and kinetic energy right now. So back to guns. Sorry for the sensitive topic. People in the old days needed a way to measure the speed of a bullet without a radar gun or a high-speed camera. They used to, real simple. Bullet mass little m at speed v is fired into a big block of wood that's hanging from a string. Little m, v, big M. So first, there's two steps to this problem. That's the trick. Two steps. The bullet collides with the block. Little m hits big M. Then, that's step one, stage one, part one. Then, after they collide, they swing up into the air. The block swings up with the bullet inside it. So of course the mass is n plus m. That's part two. Alright, in part one, what's conserved? Momentum or energy? When the bullet hits the block and drives inside and gets stuck inside the block of wood, what's conserved? Momentum or energy? conserved? Energy is conserved. It's momentum. Momentum is correct. Energy is not conserved. The bullet is making a big dent in the wood. It's getting hot. There's tons of friction. There's lots of energy being lost. Energy conserved in elastic collisions. A bullet hitting wood is definitely not elastic. The bullets just bounce out. With inelastic, energy is not conserved. But momentum is. There's no external sideways force. We can ignore the string for this short time. It's going to cancel gravity while they're colliding. So in stage 1, momentum is conserved. Energy, mainly kinetic energy, is not. And I'll write E, not K. So when the bullet enters the block, it's a collision, but it's inelastic, not elastic. So kinetic energy is not conserved, momentum is. Once the bullet enters the block, they both swing up into the air. It's kind of like a pendulum. What's conserved as the block swings up into the air with the bullet inside? Momentum. No, energy. Good job. It's energy. This is a pendulum. Pendulum is always an example of conservation of energy. A pendulum goes from kinetic to potential, to kinetic to potential, to kinetic to potential. This is like 1/4 of a cycle, from the bottom to the top. E is conserved. It doesn't stay the same. It's not all kinetic. Here it's kinetic. Kinetic becomes gravitational potential, UG. But the total, K plus UG, is conserved. The K here and the E here, or the U here, are equal. Momentum is not conserved. Changing momentum is based on impulse. What impulse do we care about? The string, kind of. More gravity. Gravity is a force, an external force. As the block swings up, it slows down. It's this momentum. And obviously, the bullet and block at stage 1, they're moving. They have momentum. When the block swings up to the highest point, it stops at the highest point for an instant in time. It doesn't have momentum. Energy doesn't have to be kinetic. It could be potential. But there's no like potential momentum. So momentum was lost. It was not conserved. Okay, so we need 2 stages where momentum is conserved, energy is not, and then finally, energy is conserved and momentum is not. So the first step is stage 1. Find, let's say, hopefully you don't get confused, this is little v. Find big V. Big V is the speed of the bullet and block together after the collision, but before they slide up. So it's inelastic in that they stick together. What's the speed together after they collide, but before they swing? Try and derive it quickly from that. Well, you set the initial momentum equal to the final momentum. The initial momentum is just little m, little v. That must be equal to the final momentum, and v. Lots of people will say, oh, little m, little v equals big M, big V. Very close. Remember we said the bullet gets stuck in the block. So the mass after the collision is not big M. It's little m plus big M. So pretty straightforward algebra. V equals little m, little v over little m plus big. Good job, Pete. Thanks. Okay, now stage 2. It's not a momentum problem. It's an energy problem. And we did so many, I'm going to just naturally assume you remember it. You of course remember the K becomes U. G. There's no springs, it's just G. And the K, it's right here. 1/2. Remember, now the mass is the combined mass. And the masses, that second mass cancel that. We still have this first mass. So, yeah. Big V is root 2GH. Hey, we've seen this before. We've seen this number many times in roller coasters and pendulums. Big V is root 2GH. Let me make sure it's a big V. However, we don't want big V. Remember when I framed this problem in a totally realistic way? It said we're finding the speed of the bullet without technology, with like the old wooden blocks and string and rulers. Yeah. So we're doing that. We're finding little v, not big V. We can find little v in terms of the given variables n, n, and the measured variable h. If this equals this, we want little v. Little v would be n plus n over n root 2 g. Yeah. So now, next time you have a gun and you want to figure out how fast the bullets are coming out of it without a high-speed camera or a radar gun or looking up online, gotcha right there. Okay. Just shoot a block of wood tied to a string and see how high it goes each. Okay, that's the ballistic pendulum. Let's see if you're paying attention. So in elastic collisions, like two rubber balls hitting each other, both are conserved. K is conserved and P is conserved. This is also a problem where there's conservation of P and conservation of energy. How is this different from that? How is this, the way we solve this, not the same as elastic collisions where we just say, oh, P is conserved and E is conserved? What's the difference? So the trick in ballistic pendulum problems is momentum is not conserved in the whole motion, and energy is not conserved in the whole motion. In stage 1, momentum is conserved. In stage 2, energy is conserved. You have to break it into two parts. That's the very big trick. Ballistic pendulum problems are broken into two parts. First, use conservation of momentum, then energy. Please don't memorize the answer. Understand why one thing's conserved in one time and the other thing's conserved in the other time. Okay, that's the ballistic pendulum. A great example of using momentum and energy and big physics brains all together. Okay, another idea, which we'll come back to in the future, but I'll just give you like a little preview for now, is center of mass. So let's say I have a nice boat, and on one side of the boat there's a nice heavy physics teacher, and then on the other side of the boat we got a baby, maybe 3 babies. 1, 2, 3. Let's keep the numbers nice and easy. 100 kilogram person. These babies are like 10 kilograms total. Alright, and let's say it's a magic future boat with 0 mass. Alright, it's not a balanced boat. If I were to get this boat in the water, it might flip. It might be bad. It's not ideal. We don't care about that. We'll care about that in the future. You can find the center of mass of this system. This is a number line. I'll call it x. X is a position of every thing. Let's say I have a very long 10-meter boat, super long boat, not drawn to scale. So everything in the picture has a position. The position of this person is 0 meters. The position of these babies are 10 meters. Hopefully that makes sense. Yeah, this person is 0 meters from the left side of the boat. The babies are 10 meters from the left side of the boat because it's a 10-meter long boat. The position of the center of mass is equal to, let's say N is man, and B is babies. It's equal to the mass of the man times the position of the man plus the mass of the babies times the position of the babies over the total mass. Hopefully this makes sense. The more mass I have, the man has, then the more the center mass is on the left side. The baby's mass at their position pulls the center mass to the right side. It's kind of an average of the position of all the mass. For this example, it's where the boat would be balanced. If I was going to balance this boat on my finger, I'd have to put my finger on the center of mass. It's all very abstract. We're not going to talk too much about center of mass until next unit, but I'm just giving the idea. This equation, we're actually not going to use it. It's just an idea. So the position of the center of mass is the sum of the mass times position over the sum of the mass. And it works in this example. 100 kilograms times 0 meters. Oh, easy. 0. $10 of baby at 10 meters is 100 kilogram. Yeah, 100 kilograms. 100 kilogram meters. A weird unit, don't worry about it. And total mass, 110. Thus, physics was done, right? So we get like 1 over 11, no, 1 over, it's 10 over 11. Yeah, that's right, 10 over 11. Which is like 1.09. No, it's 0.88. That's 10 over 11. 10 over 11. 0.909090909. It's this. 10 over 11 meters. A little less than a meter, you'd be right over here. If that's 1, right there. That's the center of mass. Why? Sorry, but now to relate it to momentum. You guys ever see pole vaulting? Pole vaulting is when these like track and field people have a big long pole and they run really fast. They stick their pole in the ground and kind of flexes and kind of launches them up in the air. I'm not even talking about that. High jumping, just high jumping. If you go into track and watch people doing high jump, they obviously are going to train their legs to run and jump really high, but they also have to learn the technique. And there's a very specific way to jump in the high jump. Watch this video and find out.
Grammarly is a digital writing assistant that caters to all types of individuals, whether you're trying to sound professional.
In the early 1960s, Dick Fosbury tried his hand at almost every sport, but never excelled at anything until, at the age of 16, he turned to the high jump. But when he couldn't compete against the strong athletes at his college using the standard high jump techniques of the time, Fosbury tried to jump a different way, backwards. Instead of jumping with his face towards the bar, bringing each leg over in the traditional straddle method, he jumped with his back towards the bar. Fosbury improved his record by over half a foot and left his coaches amazed by this strange new style of high jumping. During the next few years, Fosbury perfected his high jump style, won the U.S. national trials, and assured his place in the 1968 Olympics in Mexico. In the Olympic Games, Fosbury amazed the world with his new technique, winning a gold medal with an Olympic record leap of 2.24 meters. By the next Olympic Games, almost all the competing high jumpers had adopted what came to be known as the Fosbury flop. What's the secret behind the technique? It lies in a physics concept called the center of mass. For every object, we can locate the average position of all of its mass by taking into account how the mass is spread around the object. For instance, the center of mass of a flat rectangular object of uniform density will be in the intersection of both diagonals, in equal distance from each corner. We can find the center of mass for other objects by similar calculations, or by finding the object's balancing point, which lies right underneath its center of mass. Try balancing a broom by holding it and slowly bringing your hands together until they meet. This balancing point lies right underneath the broom's center of mass. We humans also have a center of mass. When most people stand up, their center of mass is around the belly. But what happens to your center of mass when you lift your hands in the air? Your center of mass moves upwards. It moves all the time as you move through the day, based on how your body is positioned. It can even move outside of your body. When you bend forward, your center of mass is located below your bent belly, in a place where there is no mass at all. Weird to think about, but that's the average position of all your mass. Many objects' center of mass are outside their bodies. Think of donuts or boomerangs. Now look at the Fosbury flop and follow the position of the center of mass of the jumper. The jumper runs very fast, so he can divert his horizontal velocity to vertical velocity, and jumps. Wait for it. There. Look at the jumper's center of mass as his body bends backward. It's below the bar. That is the secret behind the jump. With the old pre-Fosbury techniques, the jumper had to apply enough force to lift his center of mass above the bar by a few inches in order to clear it. The Fosbury flopper doesn't have to do that. The genius of the Fosbury flop is that the jumper can apply the same amount of force but raise his body much higher than before. That means he can raise the bar so high that even when his center of mass can't go any higher, his arcing body can. Fosbury's technique brought the high jump to new heights by splitting the jumper's body away from his center of mass, giving it that much more room to clear higher and higher bars. So the Fosbury flop may be sports history's only great leap forward that is also a great leap backward.
Wow, great video. So, even though he wasn't able to apply as much force on his body and lift his center of mass up as high as some other jumpers, he maneuvered his body, so even though the center of mass went under the bar, his body went over the bar. And he was able to be a great high jumper, whatever. Cool. Now to throw that out. That's center of mass, and we'll come back to that. But we just have to look at an application of momentum that uses center of mass. Sorry. So the position of the center of mass is the sum of mass times position over total mass. Move the m total to the other side. And since m total is basically when you treat all the objects as one, and center of mass is also when you treat all objects as one, basically m total, you can call it m center of mass. And that's equal to m. I call them m and v for man and babies, but I'll just call them like 1, 2, 3, 4, 5, whatever. x1 and 1 plus x2 and 2 plus x3 and dot dot dot. Okay, why? An amazing trick. This is position. Position of the center of mass is based on the position of object 1 plus object 2 plus object 3 plus all the positions of all the objects. Divide both sides by time. Position over time, well, if you know you're at 0, let's say at 5 seconds, you're here, and then at 10 seconds, you're here, you went 10 meters in 5 seconds, you went 2 meters per second. Position over time is velocity. Same is true here. And for no reason, I'll switch m and v. Instead of v1, m1, I'll write m1, v1. Oh my gosh, m and v. Wait, there was a reason. I was lying when I said there's no reason. It's the momentum. Now wait, what's this? The velocity of the center of mass times the mass of the center of mass, or the total mass, is m cm vcm. It's pcm. For any system of objects, the momentum of the center of mass is equal to the total momentum of all its parts. Is that useful? Yeah, there's like one kind of problem you might see that is useful. Alright, forget about the babies. Pretend they jumped in the water and went away. And let's say I'm still 100 kilograms. Let's say this boat is also 100 kilograms, to be a little more realistic. You can't really have a massive boat. So yeah. If the boat is sitting in the middle of the water at rest, and I'm also on the edge of the boat, yeah, I'm stationary, boat's stationary. Pretend it balances, because I said so. What's the momentum of the center of mass? What's that, babies? 0. Yeah, 0. If no one's moving, the momentum of everything and the momentum of the center of mass is 0. Not really a good question. If I start walking at 1 meter per second across the boat, will the boat move? Assume there's no friction or water resistance or air resistance. It was initially floating at rest, and I was at rest on top. Then I start walking. Will the boat move? Yes, it will. The boat will, when I walk, my feet apply a backward or left force on the boat. And then the boat applies a right force on me to accelerate me forward. I know this isn't acceleration, this is speed. But if I go from rest to this speed, I'll start moving. But since I applied a backward force on the boat will start moving also. How do I know it's 1 meter per second? Because I know physics. The initial momentum of the boat and person system is 0. 0 kilogram meters per second, or Newton seconds is also fine. If the man's momentum is 100 kilogram meter per second to the right, PM is man, PB is boat. 100 to the right plus something equals 0. That something must be 100 to the left. And of course, they're all kilogram meter per second because they're momentums. So I know that the boat's left momentum must be equal to the man's right momentum, so the total is still 0. If I know the momentum of the boat, I can find the speed from basic math. Cool. Did I just break energy? Could we make super fast boats without sails or engines by walking across them? No, too lazy. No, we couldn't. When you start walking, you push the boat backwards. But eventually you have to stop walking. Once I get to the end, I gotta stop. Stopping is decelerating. That requires friction from the boat. So after I finish walking, I'll stop. The boat will apply a leftward force of friction on me. I'll apply a rightward force of friction on the boat, and that'll stop the boat. So the man and the boat, they start at rest. They both start at rest. If the man walks right, the boat moves left. If the man stops, the boat stops too. In the whole problem, PCM, or P total, or P system, is 0. So that's one type of problem you'll see sometimes. It's a center of mass problem, but we haven't taught center of mass, so it's kind of weird. But for a system, the center of mass is momentum, or total momentum is the sum of momentums. So we'll do some practice. This will obviously be a 2-day lesson, at least. But we did momentum. Good job, everyone. Hopefully we understood most of it.